Hi, I'm William, reporting for the Fun Robotics Network. I'm here with Team 11146, the Barker Redbacks. They have an awesome double-jointed arm. Learn about how they use 6 motors and 1 servo, all on Behind the Buds. So, when approaching the start of the season, what was your initial plan?
Yeah, so our first prototype involved 2 linear extensions, and this was just in the first few days of the season. But we moved away from that design due to it making our robot really heavy. Last year we had a really heavy robot and it destroyed our batteries, and we had a huge amount of issues with that. So this year we went really light. The robot only weighs 7.5 kilograms, so we're quite proud of that achievement. We also decided to do the arm because it's something that we haven't really done before in FTC, and we wanted to extend our knowledge. We've done slides before, and wanted to focus more on something that we can really extend and do something different. So just having a look at the arm first, we're working with set points. We aren't using IK because we want to kind of follow the fastest route for where the motors are going. So going straight from an intaking position to a scoring position only takes half a second, which allows our autonomous to complete the first 4 samples in about 11 seconds, leaving space for us to complete a few cycles from the submersible in autonomous. The arm went through quite a few iterations with this being the first version with the pulley and the hex bore stripped out. So we moved to a gear that's inside a pulley, which kind of helped with the backlash. Kind of helped with the skipping, but not with the backlash. And then finally we moved to helix gears, which reduced the backlash quite a bit. And also, adding many wall layers here also improved the backlash quite a bit. Moving on to the climber. The climber is also designed to be really quick. So our whole climb sequence is that. So it's about a 2-second climb, or 1 second once it's touched the bar. And that's something that we've done a few iterations on making sure that it's able to climb all the way above the bar. Ollie, do you want to talk about intake?
Sure. So for intake, we obviously, with the arm, we needed the load to be really light. So the goal was to make it as small and as light as possible. So the whole package just weighs 75 grams, including the servo. It's a double roller active intake design, and it allows us to have that touch it, own it mindset. We've added a color sensor on the side so we can automate the processes in autonomous and also have that option for teleop. And also, to keep it light and small, we've decided to have a separate system for specimens. It's entirely passive, powered only by the rubber bands contained within the middle. So the driver will just run into the wall and it'll intake, and then he'll push one button and it'll go up to outtake. And then when he pulls down, the elastics pull back and the specimen can be released. Do you want to talk about the automation of that?
Yeah. So that whole process is automatically operated by one button because of how our intake and outtake system for the specimen is passive. So it's really crucial to get the timing of that correct to make sure that it's reliable every time. Some other things we've done with the arm is that we've had to include a profiled PID controller to control the acceleration from a position such as the scoring position down to the intaking position. Because of the acceleration added with gravity, that can cause the arm belt to also skip, which means that it's really crucial to kind of have limited the acceleration so that it doesn't skip. Other than that, if the arm does skip during a match, we're able to use current limiting to reset the arm. So rehoming, we firstly send this bottom stage of the arm down and then the upper stage back, so that when it hits onto each part of the robot, the current has a spike as there's no load on the motor, and that's when we can know the exact position where each stage of the arm is in, and that's how we reset the arm. Another thing we do is we use this color sensor during autonomous because, as Rory said, we finished the first 4 pieces of the autonomous quite quickly, so that allows us for time to go into the submersible during the autonomous period, and we are able to use this color sensor to detect whether or not we have a game piece using RGB. So using that, we don't need a limit switch either, because if the RGB value is greater than 1,000, then we already know that there is a game piece in our intake and we can go and continue on with our autonomous period.
Thank you very much. So you're talking about how you move the arm up. How do you use it? I see that you use the two motors to bring your arm up. Would you like to show how the two motors power the arm's movement upwards?
Yeah, so this went through quite a bit of iteration, but we took a lot of consideration into moving the center of mass of the robot all the way down. So you can see all of the motors from the robot are at the very bottom of the robot. And that really helps with reducing tipping. And because the arm is so light, when we move it around at very fast speeds, the robot doesn't even tip at all. But yeah, these motors are geared with ultraplanetaries to 45:1. And then the gears over here are a 2:1 reduction. And that gives us a final 90:1 reduction, which is kind of what we estimated would be about right at the beginning of the season with some calculations. And yeah, it's been that sort of speed has been working pretty well. The rest of it just follows through belts up into the main stage of the arm using direct drive where possible. And that's really helped with reducing backlash and reducing skipping as well. We also use open loop belt for the second stage and using custom tensioners to make sure that these belts stay tight.
I'm a huge fan of your cable management. It's some really amazing just overall packaging. So I saw on the underside of your robot, you use the three-wheeled Opti odometry. How have you found that, and what would you recommend to other teams, especially if they're using that?
So we use the Opti odometry during autonomous period, so that we are able to kind of detect where we are at all times during the autonomous period. So if you can see at the bottom, we've had this configuration of the OptiPods. It's been working quite well because we use it with Roadrunner, and we do our autonomous using trajectories. We've integrated a coordinate system into our autonomous period as well, declaring the center of the field to be 0, 0. And from that, we can just create trajectories to move our robot to where we want it to be during the autonomous period. We found it to work quite well and would recommend to other teams who are trying to start with using odometry pods.
The last question I have for you today is, what type of further improvements would you want to bring to this robot if you had an opportunity to advance?
Yeah, so a few weeks ago, we kind of decided that we wanted to try maybe adding an extra degree of freedom. So this is the differential that we would have put on the robot had we had an extra week probably. But that's pretty much a drop-in replacement for right here. So you can imagine it would allow us to move and also twist the arm, which would enable much faster specimen scoring. As you can imagine, it'll pick up like this, come all the way back, and then rotate. And then we're able to score specimens at a 45-degree angle from the robot, which means we don't have to turn while scoring. And that would greatly increase our cycle time in both autonomous and teleop. But yeah, we didn't end up implementing it just because we wanted to get everything else perfect on the robot.
Thank you so much for overall sharing with your robot. It's just been an impressive watch to see at the Australian Nationals. Thank you so much again. This has been Team 11-1-46, the Barker Redbacks.